All right. Today we're going to finish chapter 4. We're going to do chapter 4, section 6, real zeros of polynomial functions. Up until now, we've done linear equations, we've done quadratic equations. For example, if I gave you that equation, could you tell me the x-intercepts, the y-intercepts, the vertex, the axis of symmetry, oh, do we have a max or a min? And can we graph it? And you can graph it if it can't be factored. And that's what we're looking at here is not all functions will be factorable. And if they can't, that means they have solutions that may not be real, may be imaginary. So by looking at this, what can you tell me? Can you answer any of these by looking at this? With what we discussed so far in this course. Not by looking at it. I said just by looking at it, not by working it out. You know, the y-intercept is 15. So it's the y-intercept is at 0, 15. It's always a constant if it's in this form. Do we have a maximum or minimum? Why? It opens up because the leading coefficient is positive. So we have a minimum because the graph itself looks like this. How do you know the vertex?
0 to 15.
No, close. Because the 15 is the y-intercept. It's not really the vertex. The vertex itself, we have in this format, if we were looking for the vertex, we would use this formula. What is A? What is B? What is C? You have to label those first. A, B, and C are simply the integers. What is A? It's the coefficient of x squared. The coefficient of x is 8, that's B, and the constant is C. So the x value of negative B over 2A would be negative 8 over 2 times 1 is negative 4. So the vertex is at negative 4, which is also the axis of symmetry. To find the y value, we take this and plug it inside the original equation. So we take negative 4, plug it inside our equation. -4 squared is positive 16. Positive, negative is negative. 8 times 4 is 32. Sixteen plus 15 is 31. So the y value is -1. So there's your vertex. Again, all this stuff is from algebra. Is the stuff that you really shouldn't have learned from algebra. I'm just going over it, how to solve these things. So we know the axis symmetry, we know the vertex, we know it opens up, so we know that is the minimum. It's at -4, -1. It crosses the y-axis 15. Now, this is the x-intercept is the way that has multiple methods. To find the x-intercepts, we can use the following. We can try factoring. We can complete the square. Or we can use the quadratic formula. So our equation is x squared plus 8x plus 15. So my question is, which one of these three methods do you all remember? Factoring? What's the downside of factoring? If it can't be factored, you can spend for a long time trying to figure out the factors. But fortunately for this one, we can. So the first term goes in x's. What signs go in there? Yeah, so no, since the second sign's a positive, that means both signs are the same. They're both the first sign. Did we go over that last time? The procedures on how to factor quadratics? Now we look at take the first and last term. 1 times 15 is 15. What times what is 15? When I add them, I get 8. No. Which one? 3 and 5. Yes, I thought it said 8 and 5. 3 times 5 is 15. 3 plus 5 is 8. So my x-intercepts give me -3 and -5 in my solutions. So yeah, this one, the factoring method requires some cognitive effort because you have to figure out this multiplication and addition factor to figure out what was in there. Do y'all remember complete the square? Okay. Complete the square. Let me put this over here. There's a whole process. Complete the square. We're going to be using our equation. And here are the steps. First thing, set it equal to 0. In other words, get everything to one side. Make sure it's there. the leading coefficient has to be 1. If not, then divide each term by whatever the coefficient is. Fortunately for us, it is. Move the constant term to the other side. So we're subtracting 15. So we have minus 15 both sides. Remember the format, the structure of a quadratic equation, ax squared plus bx plus c. Add b over 2 squared to both sides. What is b in our case? What's that? Nope. 8. A, B, and C are numbers, no letters. So we have to add eight over 2 squared to both sides. Even if it's negative, don't worry about the sign, just the number. Because when you square it, it'll become positive anyway, so it doesn't matter. The left side, this side here, only do inside the parentheses. The right side, work it all the way out. So 8 divided by 2 is 4 squared. So I'm done with this side for right now. This side here, I got to work it all the way out. Negative 15 plus 16 equals 1. And this is where we complete the square. Put what is under the squares and the first sign inside the large parenthesis. Whatever's under the square, the first sign, and whatever's under the square. So it's x plus 4. At this stage, we can tell the vertex. It's the opposite of all these numbers. It's the opposite of +4, and it's the opposite of 1, because it's on both sides of the equation. That's the vertex. So to find the x-intercepts, solve the equation. So we're looking for x. What do we do to get x by itself? What do we have to get rid of first? Yes, but outside the parentheses, what? Yeah, we get rid of the square first. How? Square root both sides. The square root and the square cancel. Square root both sides. Remember, you have to put a plus or minus in front of the number. Square root of 1 is 1. And then subtract 4. So x is equal to -4 plus or minus 1. -4 plus 1, -4 minus 1. That's the answers. So if it's not factorable, this is one method you can use. You can use complete the square. But as you can see, it's a lengthy process. If your leading coefficient A is not 1, you have to divide by it. Now you have fractions you have to deal with. But it'll get you the answer. It'll take you some time. The third method is the preferred method. The third method is the quadratic formula. In the quadratic formula, if it's in a quadratic form, you always solve for the middle value, middle variable. Because you can have equations that look like this. That's still quadratic in structure. You solve it the same way. So if we were using the quadratic formula, we would have x squared equals -b plus or minus square root of b squared minus 4ac over 2a. Or if we did it like this, we have x equals -b plus or minus. So if it's quadratic in form, it's always the middle variable you're solving for. Remember, what does the degree tell us? The degree tells us the number of solutions we can have. And you'll always have that many number of solutions, whether they're real or imaginary. So far, so good. So those are the four methods. So for our example, label A, B, and C first. We're using the quadratic formula here. So A is a coefficient of x squared, B is a coefficient of x, and C is the constant. Plug A, B, and C into the equation. B is 8, so it's -8 plus or minus 8 squared. 4 times 1 times 15 over 2 times 1. And then solve. Then work it out. We have -8 plus minus 8 squared is 64. 4 times 1 is 4. 4 times 15 is 60. 2 times 1 is 2. -64 minus 60 is 4. Square root of 4 is 2. The reason we have two solutions is because of that. -8 plus 2 over 2. -8 minus 2 over 2. And those are our solutions. Those are our x-intercepts. So those are how we solved quadratic equations. They're great methods, they work, but they're limited. What if we had cubic equations or fourth or fifth or nth order polynomials? We couldn't do it. So what we have to do here is figure out more productive ways of solving nth order polynomials. To begin with, let's look at rational equations. F of x over g of x. The solution of a fraction is called a what? Quotient. So it's going to be a function of x. Will you always have a zero remainder? No. If you have a remainder, it's going to be whatever the remainder is over g of x. So what is the top number called in a fraction? Okay, what's another name for it? Numerator, yes, that is. What's another name for it? A dividend. That's the numerator. The bottom number is called a divisor, or your denominator. The solution is called a quotient. And the remainder is just whatever's left. So we're good? Remember, these are polynomial equations. If we multiply the entire equation by g of x, what happens? So what happens in this first equation if we multiply everybody by g of x? The g of x's cancel, so we have f of x. G of x times the quotient, and the g's cancel, so we have the remainder. This is where we're going now. This is what we're looking for here in higher order polynomials. But I'm going to show you in a second of how this stuff really looks. How this relates, this is the equation we'll be dealing with. If we had a polynomial, f of x, let's say it's x squared plus 8x plus 15. What is it made up of? What are the factors of this equation? X plus 3, x plus 5. And there's no remainder. Because if we had if we took this equation and divided by x plus 3, what would we end up with? This is x plus 3, x plus 5 over x plus 3. So these cancel. F x plus 5, which is what this is telling us. This and this and this are all the same thing. So this is what we're getting to. Is you notice that when the remainder is 0, that these two factors are the factors of our original polynomial. There are no leftovers. What would be the final answer of this one? You would have 3 goes into 11. How many times does 3 go into 11? 3 times 3 is 9. Subtract those, you get 2. So there's your dividend. There's your divisor. This is your quotient. This is your remainder. So if you have a remainder, that means the divisor is not a factor of the dividend. Four goes into eight twice. So it's 2 plus 0 remainder. So when we're factoring something, we want a remainder of 0. If we don't have a remainder of 0, then that value that we're looking at is not a part of a solution. The first theorem that we're going to look at in your sheet is called the division algorithm of polynomials. So it's saying if f of x and g of x are polynomial functions, and g of x does not equal 0, well, where and the degree of g of x is less than the degree of the numerator, then this is what we're looking at. If f of x and g of x are polynomial equations and the degree of the top is bigger than the bottom, then it could be simplified as being as this. An extension of this says if r of x, if the remainder is equal to 0, then g of x is a factor of f of x. If the remainder is 0, that means the denominator is a factor of the numerator. Yeah. 8 over 4. 8 is made up of 2 times 4. The 4's cancel, it gives us 2. No remainder. That's what we're looking for here. Is in order now to find solutions to equations, we have to find the best way to test it is by testing our denominators. So what this is looking at is g of x, q of x, plus the remainder of x, where g of x is some equation, some binomial. We have to find the value of c that fits into all that equation in the numerator. That's what we're looking for. So what does all this stuff mean? How does that relate to what we're doing here? X squared, 8x plus 15 over x plus 3. if we took the top and factored it out, we know that the x plus 3's cancel, and that'll give us our solution. Our remaining factor, I should say. So since there's no remainder, that tells us that x plus 3 is a factor of our numerator. Yeah, because we know our factors are those two. And when we divide it by x plus 3, we get that. How can you test whether a factor is real or not? So basically, here's your question. Is x plus 3 or r and x plus 5 factors of x squared plus 8x plus 15? Let's look at this in steps. Take one of the factors, set it equal to 0. Because remember, if they're factors, then they're intercepts. Those are part of our intercepts. If we set them equal to 0, so when x equals -3, if we plug that into our equation, what should that equal if it's a factor? Should equal 0. So -3 squared is 9. Positive negative. 8 times 3 is 24. 9 plus 15 is 24. We don't have to do division. We just look at the denominator, set it equal to 0, plug that value back into the function, and if the answer is 0, then we know then it is a factor. So x equals -3 is a x-intercept of that function, which means x plus 3 is a factor. So that's one way we can test it. Let's look at example 1. Find the remainder x cubed minus 4x squared minus 5. When x minus 3 and x plus 2. Find the remainder. So the first thing you have to do is what? Set these equal to 0. So x equals 3 and x equals -2. Then plug them into the equation. Three cubed is 27. 9 times 4 is 36. -27 minus 41 is -14. Mm, What that means is if we took x cubed minus 4x squared minus 5 and divided it by x plus 2, we'd get a remainder of -29, which tells us that these are not factors of that function. Which leads us to the factor theorem. Suppose f is a polynomial function of degree n, doesn't matter. Then x minus c is a factor of the function if and only if f of c equals 0. So if f of c equals 0, then x minus c is a factor of f of x. They're interchangeable. It sounds easy so far because all we're doing now is just plugging in numbers. Then we're going to go into looking at actually doing these division problems. Example 2. F of x equals 2x cubed minus x squared plus 2x minus 3. Does this function has a factor of x minus 1 and x plus 2? True or false? So we take the first equation, factor it out, set it equals 0. So we have 2 times 1 cubed, 1 squared, 2 times 1, 2 times 1 minus 1 plus 2. So what does that tell us? Yes. X minus 1 is a factor of the function. And then the second one, negative 2 cubed, negative 2 squared, 2 negative 8, minus 4, minus 4, negative 20, negative 27. Not a factor. So we determined if it was a factor or not, but that doesn't get us anywhere closer to figuring out what the rest of the answers are. So let's look at this one. Well, actually, we'll come back to this one. So we're limited. With this method is f of c equals 0. If that's great, that'll tell us we have a factor. But it doesn't tell us what the remainder of the polynomial is. So let's go back to the simple one we had. Great. We know that x plus 3 is a factor of the other one, of the numerator. We have 2 methods to divide polynomials. One is called long division, and the second one is synthetic division. You have to know how to do both of them. So long division. This is what you've been doing most of your life. For example, if we had 8 divided by 4, this is long division here. 2 times 4 is 8. Change the sign and add. So that's long division. So what we have here, we have whatever's on the bottom, x plus 3, and the numerator goes in here, or the dividend goes in here. Here, only look at leading coefficients, leading terms. What times x gives me x squared? X. So x times x is x squared. X times positive 3 is positive 3x. Change the signs and add. The first term always has to cancel. If it doesn't, you did something wrong. 8 minus 3 is 5. Bring down everything else. What times x gives me 5x? Like that? What kind of 5? Positive or negative? You have to have a sign there because this has to be a polynomial up here, a binomial or a polynomial. So we have positive 5 times x is positive 5x. Positive is a positive. 5 times 3 is 15. Change the signs and add. Remainder is 0. So that's your remainder of that equation. So that tells us this answer is x plus 5, which these are the factors. How do we know we don't have any more factors? Because the degree tells us there's only two answers. A factor is a solution, is a root, is all those mean the same thing. So we're going to have two factors. We found them both. We're done. So that's, and we'll do long division again in a second with the other example. The second method, synthetic division. Is limited. Only works if the denominator is of the form x plus or minus some number. In other words, if your denominator has an exponent or a coefficient, you cannot use synthetic division. You have to use long division. So you see how limited we are with our scope for this one. The beautiful thing about synthetic division doesn't use letters, only numbers. So our steps. Set the denominator equal to 0 and solve it. So we have x plus 3 equals 0. So x equals negative 3. You notice how the synthetic division is upside down from long division. Only use the coefficients of the numerator. So we have 1, 8, and 15. I always like to write the positions they are, because if you're missing one, you have to make sure all the columns are allocated. Now, all it is a series of multiplication and addition. The first thing, always bring down your first term. Multiply negative 3 times 1 goes there. Add straight down. 8 minus 3 is 5. Negative 3 times 5 is negative 15. Add straight down. There is your remainder. If your remainder is 0, then your answer is right here. This is the constant. And this is the x term. So we have one x and a positive 5. There's the answer. So everybody okay with synthetic division? Okay, let's look at the example 2 we just did. We had 2x cubed minus x squared plus 2x minus 3 divided by x minus 1. So first off, set the bottom equal to 0. So we get x equals 1. The coefficients are 2, -1, 2, -3. So it's just x cubed, x squared, x, and a constant. Bring the first term down. Multiply and add. 1 times 2 is 2. Minus 1 is 1. 1 times 1 is 1. Add. So we know that x minus 1 is a factor. We're supposed to have 3 answers because it's a cubic equation. 3 factors. So the second one, remember this is our constant, our x, so this is our x squared. So we have 2x squared plus x plus 3. Is that one factorable? I don't think so, no. Because since this says that both signs are the same, they're both addition. And there's no way we can have what times what is 3 that equal to make it equal to 1. Or so for right now, this one's as far as we can go. So our factored form of this one is that. How do we know how many answers we know how many answers we're supposed to get? That is the degree telling us that. But how many positive and negative answers will we get? Or will we have? To determine that, we use what's called Descartes' rule of signs, which tells us this. The number of sign changes in the original equation, will tell us the maximum number of positive solutions. By changing x to negative x and counting the sign changes. This will tell us the maximum number of negative solutions. Yeah, so basically for the original one, we use f of x, and then for the negative one, we use f of negative x. And then count the sign changes. All right, let's look at, let me put an example up here before we do example 3. Negative 3x to the 7th, 4x to the 4th, 3x squared minus 2x minus 1. How many positive and how many negative solutions will we have? Right, so we have from negative to positive, that's one sign change. Positive to positive, nope. Positive to negative, that's a second. So we'll have 2 or 0 positive solutions. They have to be multiples of 2. And the reason for this is because if you have an imaginary solution, imaginary answers have to come in conjugate pairs. So you either have 2 or 0. So in other words, if you had 6, you have 6, 4, 2, or 0. If you had 5, you have 5, 3, 1, or 1, but you have to have at least 1. So anywhere we see an x, we put a negative x. Now, when you change the x to negative x, if it has an even exponent, just drop them. Nothing's going to change. So in other words, this one's a 4, so that's not going to do anything. That one's not, nothing. Only the odd exponents will change the sign in front of them. The even ones will stay the same. And by doing this, we only have one sign change. How many solutions are we supposed to have for this equation? We'll have at most 7. This only allocates for 3. That means the other 4 will be imaginary. They'll come in conjugate pairs. Either we're going to have, we have to have one negative solution. If we have 2 positives, then we'll have 4 imaginaries. If we have 0 positives, then we'll have 6 imaginaries. So that's what it tells us. And what this will help us, it'll help us to narrow down the number of times we have to do synthetic division when we get to the next phase. So let's look at example 3. F of x equals 3x to the 7th minus 4x to the 4th, 3x cubed, 2x squared minus x minus 3. It just says discuss the number of zeros. Using the number of real zero theorem and Descartes' rule of signs, how many are we supposed to get of each? So how many positive solutions? One, two. 2 or 0. Because whatever number you get, you're supposed to subtract 2 until you can't go any further. So for positive solutions, we'll have 2 or 0 positive solutions. Oh, yeah, you're right. You be quiet. So we'll have either 3 or 1. Yes, I'm negative, positive, positive. Well, we have 3 positives or 1 positive. We'll have 2 or 0. If we have 2 negative solutions, how many positive solutions will we have to have? Remember, it's 3 plus it's 5, so we have 2. They're both going to be imaginary. 3, so we'll have 4 left, 4 imaginaries. 4 or 6. Yep. So we're going to end up with imaginary numbers no matter what we look at. But for sure, we're going to have at least 1 positive solution. All right. Any questions so far? So far, what have we done? We figured out if I give you a value, you can determine whether it's a factor or not by plugging in the values you get. We can use synthetic division, long division. So long division and synthetic will give us the remainder. If it is a factor, it'll give us the remainder polynomial we have to look for. Now, how many, if we don't know what to divide by, how do we go about and find numbers? In other words, like the first one we had. Fortunately, the first one, it was a simple one. But what if this was 5 and this was squared? If this one worked out, where would we go next? So to determine the possible factors of a polynomial, we use the rational zero theorem. What the rational zero theorem says is this: given any polynomial p of x, you have a sub 0, or a sub n, plus ax plus a. The rational zero theorem only looks at the leading term and the constant term. The rest of the stuff inside there really doesn't play much part. The size, shape, and direction of it is determined by the leading coefficient, and the y-intercept is determined by the constant. The rest of that stuff together really doesn't do much for us. So the rational number is, we'll call this one P of x, and this one Q of x. Our rational zero theorem says if we take the last constant term and the first term, the leading term, and find all factors of those, plus or minus factors of both this and this, that will narrow down from infinity down to a certain finite set of possible answers. So we've taken the entire real numbers, narrowed it down to this set. And then with Descartes' rule of signs, we even narrowed it further. Because this one looks at both positives and negatives. So let's look, for example, here. Example 4. F of x equals 2x cubed plus 11x squared minus 7x minus 6. So we have to look at all the factors of 6 divided by all the factors of 2, plus or minus all of them. 6 is made up of 1 times 6, or 2 times 3. 2 is made up of 1 times 2. we have 4 on top, 2 on the bottom, so 4 times 2 is 8. Times 2, we narrowed it down from 16, or for infinitely many possibilities down to these 16. It'll be positive negative 1 over 1, positive negative 2 over 1, 3 over 1, 6 over 1, positive negative 1 over 2, two over 2, 3 over 2, and 6 over 2. So positive negative 1, 2, 3, 6, 1/2. 2 divided by 2 is 1, which we have already. 6 divided by 2 is 3, so that one's already done. So 2, 3, 4, 5, 6. We've now narrowed it down to 12 possibilities from infinity. So what do we do with these? For each of these, we do synthetic division for that equation, because we only need to find one set, and then we can use the quadratic formula. So we use positive 1 and negative 1. Two, 11, negative 7, negative 6. So this is the x cubed, x squared, x, and 0. Bringing the first term down. 1 times 2 is 2. 11 plus 2 is 13. 1 times 13 is 13. 13 minus 7 is 6. 1 times 6 is 6. So we found our first 0 when x equals 1. So this is our remainder that we have to do. And we don't need to do any more of these because this is a quadratic equation. It's 2x squared plus 13x plus 6. We know x equals 1 is our first solution, which means x minus 1 equals 0 is a factor. We don't have to do any more synthetic division. We can either do regular factoring or we use quadratic formula. Let's see if we figure this one out. 2x, 2x. They're both the same. They're both plus. 2 times 6 is 12. What times what is 12? When we add them, we get 13. What times what is 12? When you add them, you get 13. 12 and 1. Okay, I see. Do you have questions about this? Didn't we go over this example, this type of examples last time? Yeah, so factoring this kind of equation should be pretty straightforward. So this 2x plus 12, we can factor out a 2, which gives us x plus 6, 2x plus 1, Get rid of that two. So those are my factors. X plus 6, 2x plus 1, and x minus 1. Those are my factors of that equation. So you see the whole process here is we start off with an infinite number of possibilities. We can start plugging in numbers if we wanted to. And then hopefully start narrowing it down. We use Descartes' rule of sign to say, okay, with this one, I'm going to have one positive solution. And then I'll change it to negatives. I'll get negative, positive, positive, negative. I have two negatives, which is what these. So again, Descartes' rule of sign helps me. Once I find my positive answer, I'm done with all positives. I don't have to do that anymore. I just look at the negatives. Let's look at another example here. Example 7. Find the real solutions. X to the 5th minus 7x to the 4th plus 19x cubed, 37x squared, 60x, 36 equals 0. Pause this. Has anybody bothered determining how many positives and negative solutions you're going to have? How many positives are you going to have? We have 1, 2, 3, 4, 5. You have 5 or 3 or 1. You subtract by 2 because conjugate pairs are always in twos. So subtract 2. How about negative solutions? Let's see here. So if I change this to negative, so this will become negative x to the 5th. That stays negative 7x to the 4th. Negative 19x cubed. That nothing changes there. Negative 60x. Because there's no sign changes. So we know we're supposed to have 5 solutions, so we're either going to have 5, 3, or 1. So what does that tell us? We don't have to try any of the negative solutions. When we do the rational zero, we just have to do the positives. We have to do the negatives. So what's our rational zero going to be? It's Q over P, which is 36 over 1. The factors of 36 are 1 and 36. 2 and 18. 3 and 12. 4 and 9. That should be all of them. 1, 2, 3, 4. Oh, 6 and 6. 6, 9, 12, 18, 36. Only the positives since there's no negatives. So let's start off with 1. 1, -7, 19, -37, 60. Constant x squared, x cubed, x to the 4th, x to the 5th. Okay, that's good. -7 plus 1 is -6. 19 minus 6 is 13. 37 minus 13 is 24. 36. So x equals 1 is a solution. Now we have x to the 4th. Now, whenever you find a solution, since 1 worked, try it again. Why would you try it again? Multiplicities. What if you had this 1 was 3 solutions, had a multiplicity of 3. So an answer can occur more than once. So just because it's solved it here, don't get rid of it just yet. See if it fits in this next one. One times 1 is 1, -5, 8. So we're done with the ones. Now we do the 2. -6, 13, -24, 36. 8. When do I get to my next one? So I get 3. 1, -6, 13, -24, 36. So x equals 3 is a solution. And now I got to try it on this one. Try it again. Constant x squared, x cubed. Ah, it happened again. So this one is x squared plus 4 equals 0. That's a constant, the x term, the x squared. Can you solve that one? Can you go any further? No, because if we solve this one, we get imaginary numbers. Because if we move the 4 over, square root of -4 is going to be 2i. So this is what we call an irreducible factor. Can't go any further. So our equation, what was our equation? So our equation, f of x equals x to the 5th, 7x to the 4th, 19x cubed, 37x squared, 60x minus 36, has factors. Okay, x equals 1, x equals 3, x equals 3, which means our factors are x minus 1, x minus 3 squared, and then x squared plus 4. That's our factored form. Any questions about that? Because we had 3 solutions. Remember when we did the Descartes rule of signs? We said we're going to have what? 5, 3, or 1 positive solutions? There are positive solutions, 3 of them, and we have 2 imaginaries. So our possible, all solutions were these. Those are our 5 solutions. We don't have time. We're gonna try to finish this, but we're talking about upper and lower bounds. What we do look at here is our lower bound and our upper bounds. That's a whole different discussion I don't have there. Not really used much in calculus, but we'll talk about that next time. But I want to talk about first the intermediate value theorem and how we use that. The intermediate value theorem. What it tells us is this. If f of x is a continuous function, it can either be on a closed interval or the entire domain. We'll say that on a closed interval AB. We're particularly looking at a specific space. If f of a is it's negative and f of b is positive, then there exists at least one c in the domain such that f of c equals 0. What does all that mean? What it says here is this. Yeah, if we have a function and let's say that this is A, or this is A, and this is B. If f of A and f of B have different signs on their values, that means there's at least one place between A and B where it crosses the x-axis. Intermediate value theorem says intermediate between 2 points, if they have different values and it's a continuous function, then somewhere between there, it has to be f of c has to equal 0 at least once. Doesn't tell us where it is, doesn't tell us how many we have, it just tells us that at least one exists there. So how do we find out how many and where they are? We take our domain and partition it. Into equal small sectors. And then guess what you have to do there? So let's say between these two, we have x1, x2, x3, and so on and so forth. What you have to do now is f of a, f of x1, and see if they have different signs. Then you have to do f of x1, f of x2, and see if they have different signs. In other words, what we have to do is once we use the intermediate value theorem for the entire function, we have to now do the same thing for each of these intervals. Because then there's going to be an interval, x4 and x5, where x4 is here and x5 is down here. So now we know it's between that smaller interval. Now we're between x4 and x5. Guess what you do again? Partition that one until you get narrowed down to even closer to where you're looking for. So that's one way of using the intermediate value theorem to determine and help you localize where your intercepts are. Is it productive? No. Because we just learned a much better way of doing it using Descartes' rule of signs, the rational zero theorem, factoring. But if a function is that difficult and you can't really do those, then this is your last resort. Use the intermediate value theorem to partition your domain. And once you finish that, so between x4 and x5, we partition even there. Because at each one of these points, the decimals get smaller and smaller and smaller. All right, so that's it for today. I hope I didn't confuse you all too much. I mean, in the last 5 minutes, your eyes are getting glassed over. I know, here's what we just did right now. This takes about 2, maybe 3 days in an algebra course to cover. This is actually all of chapter 4 in an algebra course. And we did it in one section. So Please try the homework problems. If you have any troubles, I would rather try to answer questions on any problems you have on there. Because I finished this chapter 4. Now we're ready for chapter 5, I believe. Yeah, that does it for chapter 4. So please try to do these questions, and if you have any questions, then we can answer those. If not, we'll see about starting chapter 5 on Wednesday. Because, well, as I say, is if people don't have any questions, then I want people to try these problems first. Because if you have no problem with them, then I thought about that. It's up to you guys. I'll let you guys decide on Wednesday whether you want to do practice problems of chapter 4, or answer questions, or start chapter 5. It doesn't matter to me. We'll vote on Wednesday. The options are going to be me doing problems. Oops, let me kill this. Me doing problems from the book.